All right, this video about net change theorem is just an extension of the fundamental theorem of calculus. One thing that I find helpful when you're looking at this theorem is reminding yourself that big F prime of x is little f of x. So in this case right here, the integral from negative a to b of little f of x dx is big F of b minus big F of a. The other thing to think about in this as well is whenever we are finding that integral of whatever that function is, if we have units here, like a lot of times like in our example right here, we're going to have velocity. So if our units are in meters per second for our velocity curve, and I'm finding this area, I'm multiplying meters per second by seconds. Well, the resulting units then of this piece here are going to be meters. So let's look at this example and kind of put some context into this. So if I have a velocity function is 3t minus 5, and I want to look at the net displacement of the particle. Displacement just means change in position. Okay, so final minus initial. If I want to call position, let's call it S of t, then that would be S of 3 minus S of 0. Well, that's going to be the integral from a to b of S prime of t dt, where this would be 0 and this would be 3. Well, S prime of t is just velocity, so I'm looking at the integral from 0 to 3 of the velocity curve. And so the integral from 0 to 3 of 3t minus 5 dt would be 3t squared over 2, or I can write that as 3 halves t squared minus 5t, and I'm evaluating that from 0 to 3. Okay, now another connection to make is if I were to integrate velocity, like this is S of t. And so when I plug in 3 and I plug in 0, I am finding S of 3 minus S of 0 using the fundamental theorem of calculus here. So that's going to be 3 over 2 times 3 squared minus 5 times 3 minus when I plug in 0, I end up getting 0. And so I get 27 halves minus 15. This is going to be in meters, and that's just going to be what I talk about for the change in distance. Okay, and that's displacement. Now, total distance traveled, that's going to be something a little bit different because my velocity equation, 3t minus 5, is negative when t is less than 5/3 and greater, or is positive, I should say, is positive when I have time greater than 5/3. So I'm going to go ahead and erase this part that I have over here and give me some room. All right, so in this scenario, I need to evaluate two different functions because if it's total distance traveled over time, then my particle's moving to the left because velocity is negative. It's at rest, and then my velocity or my particle's traveling to the right because it has a positive velocity. So I need to split this up. I need to split this up as the integral from 0 to 5/3 of the absolute value of 3t minus 5 plus the integral from 5/3 to 3, and then that's just the normal one, right? Now this is going to give me negative area from 0 to 5/3, so the best way to just kind of make this area end up being positive is know that these absolute value bars I can just multiply by a -1 on the outside, and that will take this negative area piece that I'm going to find and then plop it up here and make it positive, which is perfect. That's what I want. All right, so I have -1 times 3/2 t squared minus 5t, and that's from t equals 0 to 5/3, plus 3/2 t squared minus 5t from 5/3 to 3. All right, let's go ahead and plug in 5/3. I'm going to have this negative here on the outside. 3/2 times 5/3 squared minus 5 times 5/3 minus, and then when I plug in 0, I get 0. I'm going to add to that. When I plug in 3, we knew that that was 27 halves minus 15 minus, when I plug in 5/3, I'm going to get 3/2 5/3 squared minus 5 times 5/3. All right, I'm going to apply this negative and go ahead and simplify here. So one of these 3's cancels with one of these 3's here, but the squared still stays with the 5. So that gives me negative 25/6 plus, because remember I'm going to distribute this here, 25/3 plus 27/2 minus 15. Here I get another negative 25/6 and another positive 25/3. I could simplify this a little bit if I wanted to. Negative 50/6 plus 50/3. This does give me 25/3, negative 25/3, and then I can combine these to get 25/3 plus 27/2. I'm going to go ahead and leave it there and not really simplify much further. And that's going to be in meters as well, because that's going to be total distance traveled. So again, it's taking into account, if I go back up here to the graph, that my particle is moving to the left here and then moving to the right here. So what that could look like is you have some initial position, which I know is 0, okay, when I plug this in. So it starts at 0. Then the particle moves to the left until time of 5/3, and then moves to the right after that until 3. Well, that's why there's a difference between the displacement. If I just do the position at 3 minus the position at 0, that's different than the total distance traveled. The total distance traveled, must account for this way, back to 0, and then all of this piece here. All right, again, I'm going to clear this out so that way I have space for my last question. All right, and so here we go on this last one. If the motor on a motorboat is started at time 0 and consumes gasoline at this certain rate for the first hour, how much gasoline is used in that first hour? So let's again just think about this in terms of a graph. So if I were to graph this function, let's just call it g of t for gasoline over time. Notice that g of t's units are gallons per hour. And then in my time, I'm looking at hour. So if I multiply gallons per hour times hour, I'm left with gallons. The way that I'm going to do that with calculus is I'm going to say, let's take the integral from 0 to 1, because time is 1 hour, of the rate of consumption. And if you're ever given a rate, you should know to integrate. Okay, if you're ever given a rate, you probably should be looking at integration. All right, let's go ahead and find the antiderivative of this one. So it's going to be 5t minus t to the fourth over 4. And I'm going to evaluate this from t equals 0 to t equals 1. I'm going to plug in 1. When I plug in 0, I get 0. And so 5 minus 1/4 gallons. Okay, so 5 minus 1/4, we could write that as 20. So 19/4 of gallons would be our final answer for this problem here.